In this video, we're going to look at building a model to estimate the effect that smoking has on the odds of a baby being born low birth weight. We're going to be working with the low birth weight data, and I've already imported this data and attached it, and we've explored this data a lot so far. Now, just a reminder, we've talked about some principles of model building and variable selection earlier. We've also talked about how we want to think about each of the other variables that we might potentially include and how they might be related to low birth weight or smoking. So thinking about conceptually if variables make sense as confounders or independent predictors, and not relying just on what we see numerically when we include or exclude variables from a model. I also want to make a reminder that we really need to explore all univariate and bivariate relationships before just going into model fitting. So examining how all of the other variables are potentially related with low birth weight, as well as how they're potentially related or not related with smoking status. On that note, I want to make a reminder that when we look at bivariate relationships like plots or other summaries, some of these relationships can be masked due to other variables, or they might appear significant due to other variables. And we've talked about this concept as well in the course. So this is just a reminder that you have to be a bit careful when just looking at bivariate plots as well. So before we get into building the model, I just want to show you a few quick things you can do that will be helpful with exploring the data. So the first is the use of this pairs command. Now what this will do is make a plot of all possible pairs of variables in your data. So x1 versus x2, x1 versus x3, and so on. So let's take a look at that. Now I want to point out here, this plot is pretty messy because we have lots of variables in the data set, and also we have some categorical variables, so the plots there are going to be a little bit of nonsense. But I just want to show you this command exists and it can be useful at times. I'm also going to show you that we can notice that the variables in column 2, 3, 9, and 11 are the numeric variables. And those are really the only ones we want to make these scatter plots for. So here we can do the pairs plot with selecting only columns 2, 3, 9, and 11. Let's take a look at that quickly. Okay, and again, so this is a quick way we can visualize the relationship between all of the numeric variables in the data set. It's not always the most useful way to go, but I wanted to show it to you that it is a quick way to produce all possible pairwise plots. And you can also calculate Pearson's correlation for all of these possible numeric variables. So again, here I'm going to calculate the correlation for the data, selecting just columns 2, 3, 9, and 11, the numeric variable columns. So again, this isn't always that useful, but it's a quick way you can get some summaries to quickly check the relationship between pairwise variables. Now, if we were to go through and examine all the bivariate relationships, we'd see that almost all the variables seem to be at least weakly associated with the outcome of low birth weight, except for the FTV variable, the number of visits to a physician in the final trimester. So we can just take a look at that quickly here. We see there doesn't seem to be much difference in the number of visits for those who had a low birth weight baby and those who didn't. And if we take a look at the summary of the FTV variable, we'll notice something. Here you'll notice that 100 people did not go at all in the final trimester. 47 people went once, 30 went twice, and so on. So while this variable is numeric, looking at it, we're probably going to want to dichotomize it into just, did you see a physician in the final trimester? No or yes. Okay, and lumping all these together in one group. So the point I'm trying to make here is why it's helpful to do all these univariate and bivariate analyses before just digging into fitting your data. You'll notice things like this, that while this variable is numeric, we're probably not going to want to treat it that way in an analysis. We're probably better off dichotomizing it into, did you visit a physician, yes or no? So on that note, what I'm going to do is go ahead and create that indicator, did they visit a physician, yes or no? It's going to be very similar to what we did with the low weight indicator in previous videos, so I'm going to go through this a bit more quickly. Here we can check the number of visits for the first 5 individuals, and then we can ask this true or false question, is the number of visits greater than 0? It's going to return a true or false. And let's look at just the first 5 individuals. And so we can see no, they did not visit. 3, yes, they did visit at least once. Yes, they visited at least once. Yes, they visited at least once. No, they did not. So that worked as we expected. Now what we can do is use the as.numeric command to have the falses become zeros and the trues become ones. And then finally we can tell these zeros and ones are factors. So I'm going to do all that at once and save it in this variable ftv_ind for indicator. Now I know I went through that a bit more quickly, but we went over this exact concept in the previous video. So let's just check that that did what we thought it did. Here's the number of visits to a physician in the final trimester, and here's the indicator of if they went or not. And we can see it looks as it should, so that looks right. And we can check the class of the variable to make sure R is recognizing these zeros and ones are factors. There's lots of ways to go about fitting a model to estimate the effect of smoking on low birth weight. I think the best approach is starting with a model that you think represents the reality, so giving some thought ahead of time of which variables potentially are confounders, which ones you think are independent predictors of the outcome, and maybe refining from there. The way I'm going to go about it is I'm going to start with a model that includes all of the variables except FTV. And the reason I'm doing this is partly so we can see how the model changes when we remove certain variables, especially when we know or believe that these variables are confounders or not, or so on. So it's seeing numerically how these things behave as well. So first I'll fit a model called Model 1 that includes all of the variables except FTV. So we fit that. Let's take a look at the summary. And if we look at the coefficient for smoking and its standard error, we can see the coefficients 0.84, standard error 0.41. Now again, a reminder, when deciding if we should include or exclude variables from a model, we really want to focus on the concept of, does this variable make sense conceptually as a confounder or conceptually as another predictor of the outcome? We don't want to get just stuck on numerically how's the coefficient changing, but we're going to look at that anyways so we can try and match up the two to see conceptually what do we think this variable is, numerically is it behaving that same way, just so we can try and solidify some of our understanding of how confounders behave numerically aside from what they are conceptually. So just keep those numbers in the back of your head for now. The smoking effect 0.84 or about 0.85, its standard error about 0.41. Now I'm going to fit a model called Model 2 that also includes FTV, and we're going to look at what happens, in particular to the smoking effect. So let's fit the model, ask for the summary, and what we can see here is that the smoking effect hasn't really changed much, its standard error hasn't really changed much. So this is what we'd expect to see for a variable that is not related to smoking. And again, conceptually, I think it's reasonable to assume that the number of visits to a physician in a final trimester is not really related to whether or not someone was smoking during pregnancy. You could also hypothesize that there might be some weak association, that a smoker might need to visit a physician more often. Now we can also check using the likelihood ratio test if Model 2 is statistically significantly better than Model 1. So checking, is FTV an independent predictor of the outcome? So let's do that test here. And we can see the two models are not significantly different. In that case, we have evidence to suggest we don't need to include FTV in the model. It doesn't seem to be a confounder or another predictor of the outcome. But before we get rid of it, let's just give it one more chance because we noted that we probably want to use an indicator for FTV. So I'm going to fit a model called Model 3 using the FTV indicator rather than the number of visits, the numeric variable. So let's fit that, look at the summary, and we can see the smoking effect has changed a little bit. It went from about 0.84 or 0.85 down to 0.81. Not very much change, not much change in the standard error. We can test, is Model 3 any better statistically than Model 1 using the likelihood ratio test. Let's look at that. Again, it doesn't seem to be improving the model. So this is another indication that we don't really need to include FTV in the model. Conceptually, we thought it doesn't seem to be a confounder. It might be a weak predictor of the outcome, or we hypothesize that, and it doesn't seem to be improving the model. It doesn't seem to be a significant predictor of the outcome. So we're going to exclude FTV from the model. So far, Model 1 is the model that we're going to work with. Now let's keep going and examining some of the other variables. We can consider to try getting rid of age. And I'm going to point out, we're going to include age, right, for face validity reasons, if nothing else. If we fit a model examining some health outcome and it does not include age, our model is going to be questioned. Also, we noted earlier that age might be better represented as a categorical variable. Okay, we're not going to explore that. We have limited time in the course and we're not going to get too stuck on that idea. But we noted that age might have thresholds, right? If we're looking at the effect that age has on the risk of a low birth weight, the risk might be fairly constant for women in the kind of middle range of birthing ages, and the risk might go up or might go down for women who are extremely young in terms of birthing, or women who are kind of on the older range of birthing. So we hypothesize the risk might increase at older ages or younger ages, and it might be worth exploring working with age represented that way. We're not going to in this video. So let's just look at Model 4 where we exclude age. Let's look at a summary of the model. And we can see here the smoking coefficient hasn't changed much, the standard error hasn't changed much, indicating that age is not behaving as a confounder, which again makes sense conceptually. We don't think that age should be related to smoking during pregnancy or not. Now we can test, using the likelihood ratio test, if age improves the model statistically. Here we can see again, not a statistically significant difference. So age doesn't really seem to be a confounder. It doesn't seem to be a significant predictor of the outcome. It's not really needed in our model, but we're going to include it because age is an important variable to include in any model that's looking at some health outcome. And a reminder of this note we made that we might want to explore using age categorized into high risk at a young age, high risk at an older age, and lower risk in the middle age. We're exploring if that exists or not. And I'll tell you, on my own, I did explore that a bit. It didn't really seem to be there much. It didn't seem to be that the risk changed depending on if ages were very young or very old in terms of birthing. Now let's consider the UI, or uterine irritability variable. And first, let's think about conceptually. Do we think that this is going to be related to smoking? I would guess probably not. I don't think that the presence of uterine irritability would increase or decrease depending on if the mother smoked during pregnancy, although I don't have enough subject area knowledge to make that statement confidently. Is uterine irritability going to be associated with the risk of low birth weight? Potentially, right? We can hypothesize that having that may induce labor earlier and may increase the chance of low birth weight. That's a hypothesis. We can explore those. So let's just go ahead and fit a model that removes UI. We'll call that model 5. Let's look at a summary. And we can see, again, the smoking coefficient hasn't changed much. The standard error hasn't changed much. That's what we'd expect for a variable that's not a confounder. Let's compare the two statistically to see if UI is a significant predictor of low birth weight. You can see the p-value is pretty low. It's kind of bordering on statistical significance. And remember, we don't want to get stuck on this magic 5% cutoff of significant or not. The p-value is a tool, a guide to help us. It's not a magic number that tells us yes or no. If we look at the change in the residual deviance, it's a small change, but it's not trivial. So from this, we can say UI definitely doesn't seem to be a confounder, right? Conceptually, it didn't make sense as a confounder. Numerically, it's not behaving as one. It's kind of marginally non-significant. If we had a good argument for medically, we knew that this was a predictor of low birth weight, then we might want to include it in the model. Here, I'm going to say let's drop UI from the model. It doesn't seem to be a strong predictor of the outcome. It's definitely not a confounder. We don't need to adjust for it. But I want to make the note that you could definitely make the argument that it should be kept in the model, especially if there's a good medical reason behind that argument. So for now, the model that we're working with is model 5. So I'll just re-enter that here. It's not necessary. We've already fit that model, but I'm just going to add it so it's at the forefront of the screen. Now let's think about what happens if we try and remove race from the model. We've already noted race seems to be a confounder. The likelihood of smoking changes depending on race category, and the likelihood of low birth weight changes depending on race category. So conceptually, it fits as a confounder. Let's fit model 6 that has race removed. And before we do that, let's quickly look at a summary of model 5 again. And just remind ourselves, in model 5, which is currently the model we're going with, the estimate of smoking was about 0.86, the standard error about 0.40. So now let's look at model 6, where we consider dropping race, and look at a summary of that model. And what do we see? The smoking effect has had an extremely large change. Right, so again, this is indicative of confounding, and we said conceptually, race made sense as a confounder. Numerically, it's behaving as we'd expect for a confounder. Now, we can also do the likelihood ratio test to see if having race significantly improves the model, but I want to make a note, we don't need to do this. If we've decided that race is a confounder, we should include it in our model to adjust for it, regardless of whether or not it statistically improves the model. But I'm going to look at this anyways. So let's look at the likelihood ratio test. And we can see there, having race in the model statistically improves the model as well, aside from being a confounder that we should adjust for regardless. So just a reminder of where we are so far. We've decided that we should exclude UI and FTV. We've decided that we should include age and race. And we still have to consider the LWT, HT, and PTL variables. So just a reminder, model 5 is our model that we're working with so far. Now let's consider, can we drop HT from the model, a family history of hypertension? First, let's think conceptually, does it make sense as a confounder? Does it make sense conceptually that smoking and a family history of hypertension should be associated? I'd say probably not. Smoking and hypertension are associated. Having a family history of hypertension and smoking are probably not associated or very weakly associated at best. Does it make sense as an independent predictor? Potentially. Does having a family history of hypertension increase your risk of a low birth weight baby? Possibly. So let's fit model 7 that has HT removed from it. Take a look at a summary of the model. And what we see here, as expected, the coefficient hasn't changed, right? HT is not a confounder, so we wouldn't expect to see that changing. The standard error hasn't changed much. Let's use the likelihood ratio test to compare these two models statistically to see if HT is a significant predictor. There we can see having HT in the model is a significantly better model than not having it. Right? We can see the change in the residual deviance. So the decision to include or exclude HT can kind of go either way here. HT is not a confounder. We don't need to adjust for it. But the likelihood ratio test says it is another significant predictor of the outcome. It improves the predictive power of the model. So if it were me making this decision, I'd probably suggest to not include it in the model, as we don't really need to adjust for it. But again, you can make the argument to include it. It is another predictor of the outcome. So I just have that summarized here. Your arguments for keeping it, it's another predictor of the outcome. Your arguments for excluding it, we don't need to adjust for it. It's not a confounder, and we often want to lean towards the simpler models. And a note we also might want to consider is HT potentially an effect modifier. So just to be safe, I'm going to check that interaction or effect modification term now. So here's model 5, the model that has HT in it. Here's model 8, which is a model that is the same as model 5, but also includes a smoking by family history of hypertension interaction or effect modification. Now let's compare those two models using the likelihood ratio test. And we see that effect modification term is not statistically significant. So it doesn't appear that the effect of smoking is modified by having a family history of hypertension. So I'm going to say let's exclude HT from the model, but just a reminder, you can make the argument for keeping it in there, and that'd be a perfectly valid argument. And I also want to take a quick moment as a reminder of the difference between predictive models and effect size models. So if our goal here was to build a predictive model, where we want to say, what is the probability of a baby being low birth weight, we are probably going to want to include the family history of hypertension, and we might even consider including the UI variable. Since we're building a model to estimate the effect of smoking on low birth weight, neither of these variables are confounders and do not need to be adjusted for. So I just want to put that reminder in there that the goal of the model changes which variables we decide to include or exclude. So since I've decided to drop HT from the model, model 7 is the model we're going to be working with for now. So let's just quickly take a look at a summary of that model again and remind ourselves of the smoking effect and its standard error. Now, can we drop LWT from the model? Let's first think about it conceptually. Is smoking and the mother's weight at last menstruation or the mother's weight roughly at conception going to be associated? Quite possibly. Right? Smoking tends to lead to lower weights. If they're associated, what's the direction of that association? If they're associated, it's going to be smoking that leads to lower weights, not lower weights that lead to smoking. Okay, so LWT is potentially on the pathway between smoking and low birth weight, or it's potentially mediating that relationship. So let's think of it conceptually that LWT may be a potential mediator and see what happens numerically. So let's fit model 9 that removes LWT. Let's look at a summary of the model. And we can see here the smoking effect is a little bit higher when LWT is removed. And let's think of it conceptually, what's happening. So the smoking effect is 0.90, and when we include LWT, it goes down to about 0.86. So some of the smoking effect is going through the LWT variable. LWT is mediating it. And when we include LWT, the smoking effect decreases because some of the smoking effect has gone through LWT and is now captured in the LWT coefficient. Let's compare the two models using the likelihood ratio test to see if LWT is a significant predictor of the outcome. Again, it's borderline statistically significant. So we might not want to include LWT in the model. Also, recall that we noted LWT is not linearly related with the log odds of low birth weight. And we decided it might be better to use an indicator variable. Is the weight less than 110, yes or no? So for the time being, I'm going to keep LWT in the model, and later we're going to look at replacing it with LWD, the indicator, to see how that works. Now a final decision, what should we do with the PTL, the indicator of previous premature labor? While it might be nice to have a bit more medical info on this variable, we talked about it previously that PTL might potentially be a mediator. So the effect of smoking on low birth weight likely goes through PTL. Smoking increases the risk of having a previous premature labor, and premature labors increase the risk of having a low birth weight baby. So we already talked about this idea previously. It's worth noting there is an extra layer of assumption that if the mother's smoking during pregnancy, that she has been smoking for a while. We're removing the possibility of having had a previous premature labor as a non-smoker and then beginning smoking and then having another pregnancy. But that's much less likely and going to be far fewer of those. So it can make sense conceptually to think that smoking has a direct effect on whether or not the mother has had a previous premature labor, and previous premature labors have an effect on the risk of low birth weight. Although it's important to note we might need a bit more medical knowledge here. So let's just take a look at what happens when we exclude PTL from the model. So I'm going to fit a model, I'm going to call it model 10, that has PTL removed. Let's take a look at a summary of that model. And we can see when PTL is not there, the coefficient for smoking is a bit higher. So let's just put them side by side. Let's compare the coefficients with model 7, which is our model so far, and then model 10 if we remove PTL. So again, what we see happening here numerically is indicative of mediation. When PTL is not there, the smoking effect is 1.05. When we include PTL, the smoking effect goes down. And the reason for that is that part of the smoking effect is going through PTL. And when PTL is included in the model, some of the smoking effect is absorbed into there. So based on our discussion, I'm going to exclude PTL from the model. I believe that it's mediating the relationship between smoking and low birth weight. And again, I want to have the reminder here that if we were building a predictive model, we might make a different decision. So let's just compare model 7 and model 10 statistically. And we see PTL, an indicator of a previous premature labor, is a statistically significant predictor of the outcome. Or the residual deviance goes up a lot when we exclude PTL. So if we were building a predictive model, we'd probably want to include this variable. Now at this point, the model that we're working with is model 10. Model that has smoking, age, LWT, and race. So I'm just going to remind you of that model. Let's fit it here and look at a summary of it. And we can see the smoking effect and its standard error with the variables that we've decided to include or exclude from our model. Now you'll recall we talked about the LWT variable earlier, and we noted that the relationship between LWT and the log odds of low birth weight was not linear, and we thought we should replace it with an indicator if the weight is less than 110, yes or no. So let's just explore that. And I'm going to create the indicator here again as we did before. So we're just going to ask, is the weight less than 110, yes or no? Convert those to 0 1s, tell R those are factors, and store them in an object called LWD indicator. So what I'm going to do is replace the LWD variable with its indicator in the model. And this is going to be the model we're working with so far. And now we're going to compare that to a model I'm going to call MOD that has the LWD indicator removed. Let's fit that. And let's compare the coefficients from the two models. This is one that has the indicator and the one that doesn't. And again, we can see when the LWD indicator is not included, the smoking effect is higher. When the indicator is included, the smoking effect gets lower. And again, we noted why we think that is. Part of the smoking effect is going through the LWD indicator. So when that variable is included, some of the smoking effect is captured in there. So this gives us some evidence that LWD is behaving numerically like a mediator. Let's just quickly compare the odds ratios when we exponentiate. So when we have LWD indicator in there and when we don't. Here's when LWD indicator is in the model, and here's when it's not. And it's a bit comforting to see that it's not a big difference if we include the indicator or not. So I'm going to choose to exclude the LWD indicator. Again, I believe that this is mediating the relationship a bit. So we're going to work with this MOD model. Now that we've decided which variables to include or exclude in terms of confounders, mediators, and independent predictors, let's examine interaction or effect modification terms. In health research, age, biological sex, and race are often effect modifiers, so let's explore some of these. First, we'll check the interaction or effect modification of age with smoking. So I'm going to fit a model I call model A, and this is going to include a smoking by age interaction. So let's fit that model and use the likelihood ratio test to compare these two. And we can see they're not statistically significantly different. So this interaction or effect modification term is not significant. So conceptually, it probably didn't make too much sense that the effect of smoking would change with age, but it was one worth exploring. Now let's check the interaction or effect modification of smoking with race. So does the effect of smoking change depending on race category? I'll fit a model calling it model B, including that term, and compare the two using the likelihood ratio test. And again, we can see this effect modification term is not statistically significant. And we also noted earlier in the course that this may potentially be due to the small cell counts in each of the race categories. So that might be something worth exploring more if it was a question of interest. We've decided not to include any interaction or effect modification terms in our model, so this is going to be our final model. We're going to look at the effect of smoking on low birth weight, and we're going to adjust for age and race. So let's just fit that model again so it's on the screen here. We can look at a summary of the model. To get the adjusted odds ratio, we can exponentiate the coefficients. We can see this is the odds ratio of smoking adjusted for age and race. We can put confidence intervals around that using the confint command. Here's the 95% confidence interval for the smoking odds ratio. And I'm going to bind the odds ratios and their confidence intervals together and round it to 2 decimal places just for neater presentation. So we can see the smoking odds ratio is 3.01 adjusted for age and race. Here's the 95% confidence interval. And then just a quick reminder of the unadjusted odds ratio, when we fit a model estimating the effect of smoking, not adjusting for anything else. The unadjusted odds ratio was 2.02. So now we have all the stuff we need to interpret the effect of smoking on the risk of low birth weight.